This is when the first piece of a program, saw the light of day. So around, I don't know the exact date, 1935, Professor Godeaux said, let's take the group of order 5 acting on P3. So I write that 1/5 for the group mu5, 1, 2, 3, 4, acting on P3, and take an invariant hyperspace. For example, the Fermat quintic. And in there I take my quintic hypersurface invariant under that, and you do y5 divided by the, and this is x. And this is a surface with kx ample and with the smallest invariance, pg equals 0, because there's no invariant form there, and k squared equals 1. So it says somewhere that k squared equals 5. And this guy here has, this x has k 0 of x contains z mod 5. So z mod 5 is the character group. Z mod 5 is where these guys, 1, 2, 3, 4 live. Yes, so I'm insisting here, I'm writing mu5 and z mod 5, which of course are isomorphic of the complex numbers, but you should think of them as Pontryagin dual. When you get characteristic P, there'll be a Cartier dual. If you one of the rules of life is if you enjoy doing something, you should do it again. And so you can perfectly well say 1/5 of 0, 1, 2, 3, 4 divided acting on P4, and then the hypersurface there, and then you get a Calabi-Yau with the smallest possible value for the degree. This has got an ample divisor A with A cubed equals 1, and it also has Z mod 5 in its pick 0. Or, the title of this conference has higher dimensional geometry, so I can write 1/5 of 0, 0, 1, 2, 3, 4, and then I get a finite 4 file. With 5 times 1/5 of 1, 2, 3, 4 singularities, right? Because the invariant quintic hypersurfaces will necessarily meet this locus. Yes. So another little point I want to remark, which will be important in the future. This is the regular representation of mu5. Yes. So I started this. I don't really need this.
So you it's not strict Calabi-Yau. With fundamental group not zero.
With a fundamental group and pick 0.
Fundamental group is 0. No.
The fundamental group is Z mod 5.
Yes.
Yeah, it's either the same as pick 0 or it's a character group of pick 0. So if we're in characteristic P, then we know how to write down three group schemes of order P, which are defined over, define that field at P, and they're unique up to isomorphism over aspect closure at P. Yes, there's such small subtleties which I'm trying to describe. But you notice that they're also basically very similar. So X to P equals 0, you might think this is a stupid thing to write down. What we're doing is we're writing 0 here, and then we're writing a little infinitesimal label. So here we're writing 1, and a little infinitesimal label of 1. And so what's the difference between these two? Well, I'm going to write down, I can write down, if I write down the map, A1 goes to A1, given by X goes to 1 plus X. Right? Or later on, this will be 1 plus TX, with T a deformation parameter, non-zero. Then this is an isomorphism of the underlying group scheme of this and of this. However, it's not the group homomorphism, but these groups are not isomorphic. So there's something called the Tate-Oort group. The Tate-Oort group scheme. This is a sort of major project. You're not going to actually look at this thing for the web address of the, it's my website plus CMP. So there's something called the Tate-Oort group scheme, which combines these three guys in one deformation family together with the cyclic group 5 in characteristic 0. Right? And so I want to, let me just sort of say this in a little bit of detail. There's the ground feature, the ground ring Z. Then there's the base ring B, which is Z of capital S and little t divided by P. Right? P is the equation S T to the P minus 1 plus P. So, this is sort of completely harmless little thing. I'm taking a variable t and making the, what do you call it, t and t to minus 1. And I'm making a little subring there where I only allow so many denominators of t. Yes. And so, take spec of this ring, you get spec of Z, and then here is the fibers over P not equal, over not equal to P. And then over P, I get this little picture, right? The S axis and the T axis. And there's this kind of little base change to it. So the group of cyclic group of P minus 1 is the common automorphism group of all three. Right? And then over this, I have the coordinate ring of T and P. And this is B, X. So X is a coordinate in the A1 axis, in the A1. All three of these groups are contained in one and the same A1. Yes? So some of you might prefer to write this as a hot Faucible movement. So X maps x maps to x tends to 1 plus 1 tends to x, right? But this is the group law here is the restriction of a polynomial map from A1 to itself. Yeah. So I'm going to write this bxt, 1 divided by an equation. And the equation is x to the p minus s t to the p minus 2 x to the p minus 1 minus other stuff here, and then minus sx. And the other stuff here is summation of binomial coefficient p choose I divided by p times t to the I minus 1 x to the I. So, the thing to notice about this polynomial is it's a monic polynomial of degree p. So if I over b itself, or over any pullback of b, this will be a free algebra of rank p. And then you'll notice that the linear term there is s times x. So if s is invertible, this is an étal. This is a separable polynomial. Yes, and if t was 0 and s was p to the minus 1, it would be giving you exactly this equation. Yes, and so here I have the t split. This is s to the p minus 1, that's a pullback of order p minus 1. In order to be able to write down the group law of this, and the group law is that this thing here is called the Cauchy-Miramanov polynomial, and it's interesting for a number of reasons. But what it's doing is it's handling the isomorphism that I had over there between, what you need to do if you want to see an isomorphism between the group mu p and the group z mod. Obviously, we want to choose an interunity, and there are subtleties about that. I'm not going into that, it's a second paper. Yes, the group law is x1, x2 maps to x1 plus x2 plus t times x minus 2. Yes. So, a kind of better way to write this is the group 1, 0, x, 1 plus tx contained in GL6. Yes, so if I multiply these two matrices, I'm doing 1 plus tx, 1 plus tx1 times 1 times tx2 minus 1 divided by t. So this thing here is, if t is invertible, this is 1 plus tx1, 1 plus tx2 minus 1 divided by t. So what it is this isomorphism, right? I make the translation, x goes to 1 plus tx, I do the multiplication there, and then I undo that by this minus 1 divided by t. Yes, but however, this thing works even if t is not invertible, this is not very fun t, so. Okay. So over about 30 years or possibly 40 years, I don't know, Lang, Bill Lang, student of Mumford, Miranda, and Leachner showed the three groups that you would see. Acts on three, essentially by the regular representation. This is the regular representation divided by the trivial representation. Right? And you can find an invariant quintic and so that's like this y. And when I do y mod x, I get a non-singular surface with kx ample. X squared equals 1. And pick 0 contains the dual root scheme of these things, contains mu p or alpha p or something. Yes, so they gave these constructions, which is not very difficult, but Lang was a student of Mumford, and this was about the time Mumford and Bombieri were doing illegal stuff. So about 10 years ago, Young with some help from me, put the three together as so I didn't quite finish the narrative here. There's a group action here. When T is invertible, the group is isomorphic to mu p. But it's isomorphic by this truncated exponential. Yes. When F is invertible, it's an étale root scheme. It's a form of FP plus. It's a form of ZP. It's ZP where you've got the 0, which are the roots of 0, and all the other elements are conjugate among themselves. That's what this P9 is. Yes. And then if both S and T are 0, obviously that is the FP plus. So how am I doing for time? So Kim Soo-young was a student at Seoul University at the time I was a professor there. She's a student of what's his name? Young-nam. Young-nam Lee. And also right, so if I've got a group, a group scheme, it has a group of automorphisms, and there's something called the holomorphic completion or something, where you make a kind of affine extension of the group by group of automorphisms. So in other words, there is a single family of quintic surfaces that contains these constructions of Lang. Okay, so I want to do the three quotient case today. And so there's some mathematics and there's computer analysis. And what you want is it's not finished. This is the work which is in occasional progress. So first of all, let me tell you the characteristic zero constructed over the complex numbers of Z-3, usually Z-3 portion of Godeaux. So this is a sort of strange construction. The conference is called higher dimension geometry. So I'm going to write down the 9-dimensional graphic containing 13-dimensional space. Yes. So I'm going to write down the hypersurface minus 1 over 2 by 3. So again, if you go to that website, TOP, you have to type in after the address Slava72 .text, right? So this is the whole construction. I mean, I'm not proposing you read this. I'm just telling you that's where you find it if you want to see it. Can't read my hand. But so I'm going to write y1 by 2 by 3 plus r1 times y1 x2 x3 plus, and then cyclic terms r2 y2 x1 x3 and so on, and then plus s times x1 x2. But maybe I just want 1, 2, 3, 3, 4. So the group action on this is the cyclic rotation, the 3 cycle, 1, 2, 3 of these. Yes. And so, you know, this is a hypersurface, G. B of G is a hypersurface in, I think it's 13, it doesn't really matter. Yes. And it contains inside it 3 different completed sets of hypersurfaces. Yes, and so I have this theory, there's a paper by Stavros Papadakis and myself, called unprojection. There's an unprojection. There's about 50 papers by Stavros Papadakis. And so what this is I can make a construction, I can make a new variety containing whose equations, whose ideal equations contain this G, but where this variety xi, yi is sent to infinity. So I'm going to write down an equation that a rational function on this that has a pole along xi, y. Right? And so let me just do it for 1. All of that stuff is divisible by y1, and all of this stuff is divisible by x. Right? So I'm going to, this is called the ax plus y. I'm going to write down z1 equals something divided by x1. So that's all the terms here divisible by 1. Y, 2, 1, 3 plus 1 equals And then there's probably a minus there somewhere. Let me, between friends, what's a few minus? Anyway, maybe I'll put a minus. Two, four, two. Not the same as in the yes. So I've written down here equations x1 z1 equals something, y1 z1 equals something. I think that's on the. You can easily figure out what these are. And then there's a threefold rotation, and then the equation z1, z2 equals something. And in computer algebra, you can deduce this by taking this idea, the idea generated by these things, and doing colon ideas. So, in other words, allowing, I think the equations I have here, if I multiply this by z2, then eventually, after subtracting off some more of the equations, I can cancel the x1. I'm talking here somebody who does computer algebra. Yes. However, there is a theorem here. The theorem is called the unprojection theorem. It guarantees that I can write down this equation z1. So in practice, I'm going to write down a 5 by 5 symmetric matrix, which is there. X1, X2, X2, Y1, 3. I can't read it from here. X1, X3. Z2, Z1 or minus Z1, I don't know. Minus Z1, minus 2, 3. And then this computation by S, X3 times so most of us can do 2 by 2 minors in our heads, right? So 2 by 2 minors that. But 4 by 4 Pfaffian is more or less the same thing. I do this times this, minus this times this, plus this times this. And so that's this equation. Yes, and so 4 of the Pfaffians here are among these 4 equations there. And then there's the equation involving Z1, Z2. And that's the thing that's written somewhere in here. So, if you're interested in seeing the details of this, then download this file. At the end of the file, there will kinds of gibberish, editing facts I haven't seen out yet. Okay. So, what this constructs is a variety is a with all of these coordinates, 3-dimensional coordinates. So I'm going to use, I'm not really interested in this yet, I'm really interested in its projectivization. So I want this to be, I'm going to give x's to 1, y's and the r's to 2, and the z's and the S degree 3. So this is a corner of index 9 point. Corner of index, I think it's 12. And so now I'm going to do.
Very much. I understand the rates and limitations, but we have 4 different tests.
No, it's only one. There's 1, 2, 3, 6, 3. So the reason for writing about this, the R's, I'm thinking of the R's as being varied, as being parameters. Right, so let me define a 9. So if I set Ri is the general combinations of X1 the XI1 of 2. So I take all of my elements in XI1 and I make a general combination. And the S is general cubic. So when I impose the Z mod 3, the 3 cycle symmetry, I want these 3, R1 to go to R2, it's R3, it's back to R1 under the 3 cycle. It's going to be invariant. Yes. So this I've cut the 9 point down to. Okay. This cuts F down to door frame index 1, and it turns out that it has 3 times 1/3. 1, 2, 2, 2, 2, 1, I think it is. 1, 1, 2, 4. So I'm not really going into this, but if you think about this P2, the intersection of all of these equations with that P2 is just Z1, Z2, Z1, Z3, Z2, Z3. So that's just the 3 coordinate points. And by construction, the whole point of one of the whole points of unprojection is that this Z1, at the point where Z1 is 1, X1, Y1, Z2, Z3 are implicit functions given by the implicit functions. And so this is an orbifold point. It's a non-singular variety that happens to a method with maximum strength. So this is a nice non-singular variety. And now if I add to that, I know all about its equations, I know its Hilbert series, maybe the Hilbert series is written there. I'm not insisting that you read it, but you will be able to read it. So if I said also X0, X1 plus X2, plus X3, 0, this gives the surface with PG equals 2, plus 3. And I can divide it out by U3, and by, in this case, by the cyclic root of order 3 set mostly, acting by the 3 cycle 1, 2, 3. Yes, so this is a Godeaux of order 5. So, you know, I know it's bad manners, but this is computer algebra. The file for running this is in this Java 72 file. You can do this yourself, right? So I just cut and pasted the thing from my website into the online Magma calculator. Yes, so I write out the equations I've just told you. I've made in computer algebra, if you need generic variables, you take a finite field and you take random elements there. Right, so I'm taking the field of order 97. 97 is a nice prime number. I'm taking random linear combinations for these and then, you know, I pop the question at the end, is this guy non-singular? Yeah, this says it's a surface, it's irreducible, and its Jacobian subrank scheme is the empty set. Yes. And then I said I was working over the complex numbers. Instead of doing that, let's work over a finite field of order, let's say 3 to the 6. 3 squared also works. Yes, and then you know I have to calculate the invariants, and so these are the cubic contours are invariants under the action. And again, I get a non-singular variety. So this is an analog of the construction that Miranda gave, but the Z1 5. So this will have Z1 3 there. It gives Godeaux surface with P equals 1, P equals 1, 2, sorry, H1 of X. And there's this little U3 contained in its fifth zero. Yes, and so, you know, this is, I almost wrote Q here, meaning irregularity. Because the irregularity of the surface is the dimension of the decoder of the algorithm. So there isn't an algorithm, right? There's this tiny little group scheme contained in X0, which disappears when you make an état coverage. So that's the easy part. So maybe how do I get rid of this? Oh, yes, okay. Sorry? I'm trying to get rid of the screen so that I can use the back. It's tricky enough. So let me talk a bit more seriously about this taper roof and what I want to do with it. So I've got S C squared plus 3 equals 0. So in order to be able to see all of the degenerations of the group of the three characteristic zero, I have to allow this factorization of the prime three. Right? And there's this, the group is contained in A1 of X over the base cube B. Yes, and it's 1, 0, X, 1 plus 2. So, you know, I wrote down this equation, which in this case is x cubed minus s t x squared minus sx. Yes, and so, you know, you have to persuade yourself that if you impose this equation, then this 1 plus 1x, 1 plus tx cubed is the identity. Yes, and so, you know, I mean, try doing this during the, it's not trivial. It's easy if you choose to use complete math. Yeah, it's not difficult, but you can do it. It's written in the paper. Okay, so, you know, there's no point in being a group if you're not acting on something. Right, sorry, I have 5 minutes. And so the regular representation is this is the given representation. The G. This is the group is given to us as a subgroup of 2, so it has a 2-dimensional representation. Right. The regular representation is S2 of the given. Right. So this is the regular representation of the group is the coordinate ring of the group. So the coordinate ring of the group is based by 1x squared. Yes, and so if you look at 1 x squared, you get the matrix 1x 1 plus tx, and then x squared 2 into 1 plus 2 x into 1 plus tx, and then 1 plus tx squared. Yes, and so you all know that if I've got a 3 cycle of objects, so let me use some letters that I haven't heard yet. So M1, M2, M3. Then if I want to make this not into a permutation representation, but into an eigenspace representation, I have to do, I'm going to write omicron 0 is M1 plus 2 plus M3, and omicron 1 is M1 plus omega M2 plus, this is in characteristic 0, omega squared M2 plus omega M3, and omicron 2 is M1 plus omega M2 plus omega squared. Right, and then this makes the same representation into 1/3 of 0, 1, 2. Omega is a cube root units in the complex numbers. But, and so conversely, M1 is a scale of etc. So this transformation was written down by Kumar around 1860. I don't know the history, although most people now know it as Hilbert theorem 90. Yes, so you can transform between the bases. So this doesn't work very well in characteristic 3. So instead, on the other hand, I can use this to make, I can, if T is non-zero, I can diagonalize this matrix, get eigen vectors by, I hope I will get rid of this. It's, you know, it's written down in the paper. This is going from which to which. So, so suppose I've got, you know, U1, U1, U2, U3 here with that representation. So the eigenvectors by setting, oh my God, what's the next letter? B. B0 is U. So I'm going to write B0 is B1 is U0 plus T times U1, and B2 is U0 plus 2T N1 U1 plus T squared U2. And you know, if you want to continue this matrix down, it would just be binomial surface all the way. So if you want to do the thing you did with Young, you just get the same but with a bigger matrix. So now these are eigenvectors. To take the this crazy equation I have, minus the equation for this variety here, translate it to characteristic 0 into eigencoordinates, and then I translate it out in characteristic P into these coordinates. So the thing you notice about this is a perfectly nice basis where T is invertible. Right, however, where T is 0, it doesn't work very well. Yes. And what you do is you take all the equations of character and you jiggle them around until they're divisible by power. Take the funny equation before, you can write it in the, then this is modulo defining Plato scheme. It's identically divisible by T to the power of 6. And so this already gives you some of the equations I need. And you know this. So you know, I often hear either alchemists or geologists saying that an inseparable equation, in characteristic P, an inseparable map of DEP is somehow pathological, whereas the settlement equation is virtuous, is good. And that's just complete nonsense. The great thing about this group is when T is not zero, I get to do mu P. So mu P actually on the right. If you do mu P actually on a vector space, the quotient is a product variety. All the rules for calculation are that. Mu P is reductive. So the total group, when T is invertible, is a reductive. You do all the calculations using balloons, exactly as if you were just doing correct numbers. Yeah. So at the end of it, we have to do a non-singular calculation, and then when we set S and T equal 0, we get the best possible answer. There are quite lots of subtleties that I've not gone over. 50 minutes is a short time for quite a complicated topic. So let me finish there.
Any questions for Miles? No, thanks again.